Alright, hi guys. Today we're going to be talking about the convolution operation, which is at the heart of a variant of a neural network called convolutional neural networks. So let's get started. And just before, you can find a lot of the images that are included in this presentation in the previous TJML lecture on this topic by Kevin Fu. Okay, so before getting into the technical details of the convolution, I just wanted to give some historical context. The idea of a convolutional neural network has been around for a fairly long time in relative to a lot of deep learning research, right? It's not like a new idea, but they really weren't able to get super good performance with these models for a while because of lack of computational resources and lack of data. But as we've seen, it's sort of like a trend with a lot of deep learning based techniques with increased computation and more data. These models perform extremely well. And in 2012, that's what this research group from Toronto actually found. This these three people in this picture on the bottom right. This is Jeff Hinton, Ilya Sutskever, and then Alex I can't pronounce his last name. Uh, it starts with a K. And basically, they're from the University of Toronto, and they entered this model in a competition known as the ImageNet competition. And in the ImageNet competition, there are 1,000. There are thousands of categories of images. You can see some of them here. And the goal of the competition is to get a program to essentially output the category of like which category a certain image belongs to, right? So if you get an image of a dog, you have to output dog. Um, so, uh, you know, people were trying a variety of approaches before that, and progress sort of stagnated. I mean, you can see uh, in 2010 and 2011, we got 28 and then 26% accuracy, and then all of a sudden there was this huge jump down. Sorry, this is not accuracy. This is I think it's you want less of this metric. So if this was, I think it's like some measure of error. I don't have. Should probably find the y-axis on this graph. But this is a good thing. Going down is a good thing, right? Um, uh, so um, you can see that there is a huge improvement between 2011 and 2012, and this was when AlexNet was introduced. Um, and so since 2012, there's been like a sort of huge interest in a lot of deep learning techniques. So this paper was it sort of kickstarted that, you could say. I mean, there was a lot of other stuff going on at this time too, that revolved around these sort of deep learning techniques, but this was the one that people sort of were like, whoa, okay, like this is something. Oh, and just a side note, Jeff Hinton is sort of recognized as um, uh, the creator of neural networks. I mean, along with several other people, and Ilya Sutskever was his postdoc. I think when they were doing this, or like they were working together, and now Ilya Sutskever has founded OpenAI, which has, he's like a founding member of OpenAI, which is one of like the leading AI research organizations in the world. Okay, so moving on from that, let's talk about what is a convolution. So the conceptual idea, so a convolution neural network is very similar to a neural network, except it relies on this operation known as the convolution. Um, and the basic idea of why we want to do this, like the motivating factor, is that, in images or in uh, data types like images, you can have pixels that are in one, you can have like data points that are in one area of the image, but then they're not very related to other pixels that are super far away, right? I mean, in an image, the pixels and the pixels that surround that pixel are usually like closely related because they all are representing some sort of similar sort of part of the image. But if you take a pixel from the top left of an image and then a pixel from the bottom right of an image, chances are there's not going to be much like they're not going to be too related because they are from different parts of the image, right? So if you have a fully connected neural network where every neuron in one layer is connected to every single neuron in the other layer, what ends up happening is during training, the neural network has to learn that some of the neurons don't really depend on other ones in the previous layer, right? Because if you think about like each neuron looking at a specific part of the image, then you don't really want to have, at least in the initial layers, there's really no benefit in having um, neurons that are looking at the top left corner of an image talking with the ones in the bottom right, because the neurons are looking at like such small portions of the image that there's really no relationship between what the two things are seeing yet. So by using a convolution operation to essentially carry out computations, we basically, borrowing a term from neuroscience, we define what are things called receptive fields. And receptive fields are sort of like areas that each neuron will look at. And by doing so, we drastically decrease the number of parameters and basically have an inbuilt mechanism to tell our network, hey, you want to look at pixels that are close together. And you don't really want to worry about faraway pixels in the initial layer. So don't worry if that didn't make sense. Like we're gonna go into the technical details, throughout this lecture. But just note that the main reason why convolutions gain so much, um, they're so much better than fully connected networks, is that they basically allow for us to encode, like pre-encode um, the spatial relationships that we would otherwise need to learn in a fully connected network. Okay, so what is the convolution? The convolution is an operation, like a mathematical operation. It has numerous applications, from signal processing, audio processing, and it's used a lot in differential equations. Um, for our purposes, we're not going to talk a lot about the mathematical theory here. We're going to take a very sort of like simplified view of the convolution, and just know that there is a lot of mathematical theory behind this idea that we're not going to get into. We're just focused on the application of this operation to neural networks. So in this animation that you see here, um, the light blue image, the light blue sort of set of squares is our image, and then the dark blue square is a kernel. These are sort of like our weights. The dark blue area is similar to the weights of our regular neural networks. And what ends up getting outputted from carrying out this convolution operation using this kernel and using this image is something we call a feature map. Okay, and what ends up happening is every time you sort of place the dark blue area onto a section of the light blue area, you multiply each of the elements that are like corresponding in position, and then you take all of those products and then you add them together. So we're going to walk through a quick example on the next slide. So let's say that we had this 4x4 image matrix here, and this is our kernel matrix, and we want to perform the convolution operation using this image and this kernel. Well, what we would end up doing is, okay, we first take this 3x3 matrix, place it over here, right? And then multiply each number with the other number from the kernel that matches it in position. So doing this for the first sort of quadrant here, we can, not really quadrant, but this first like area, we would do 4 times 1, right? Because when you slide this over, 4 would be like on top of or under 1, depending on like the order. But 4 times 1 plus 2 times 2 plus 0 times 3 plus 3 times 4 plus 2 times 5 plus 3 times 6, and so on. And this is the full thing, and hopefully I didn't make any arithmetic mistakes, but the answer would be 142. And so now we have this sort of number, and then to find this number, we'd essentially just slide this over, and do the same thing. And then to get this number, we'd place, the box would go like this. And then for this number, the box would go like this, right? And so maybe take the time to do that, at least for like one of the boxes. I mean, it's a pretty simple idea, but uh, there's no harm in doing it. And then also note that we're going to talk more about this in the next lecture, but actually here we have a stride of 1, which means that, from here we move 1 to the right, and then we move 1 down. But in some, this is actually a hyperparameter. You don't have to move 1, you can actually move 2 or 3. Now in this example, it doesn't make sense to move 2, because then you'd be like off the screen, and there are ways to deal with that we'll also talk about in the next lecture. But just keep in mind that you can have a stride of more than 1. It's just in this example we kept it 1. Okay, so I'm gonna go to the next slide now, so maybe pause if you haven't worked through it yet. Okay, and these are the values for the 3 other entries. Okay, so to get some intuition as to what the convolution operation is doing, it's probably helpful to look at some examples. I'm gonna talk about this briefly, but it's not really the main focus. There's 2 other examples that I think will help you understand better. But this kernel, I mean, just first think about it. What do you think it's doing? Okay, so given that all of these are 1s, if we place this kernel on some position on the image, what is it going to do? Well, it's just going to sum up all the pixel values. It's going to sum up all the pixel values of a certain pixel and all the pixels around it, right? It's going to take the sum of those, because we're just multiplying by 1, so all the values just stay themselves. And then whatever sum you end up getting, you divide by 9 at the end. So what this is doing basically is, for each pixel in the image, it's taking that pixel's value as well as all the 8 surrounding pixels, and then taking the average of all those values, and then replacing the original pixel value with the average of all of the surrounding values. And what that ends up doing is essentially like smoothing out the image, so you don't have sort of like outliers in terms of all the numbers basically get closer together. And what ends up happening is that ends up blurring the image a little bit. You lose a little bit of like the sharpness of the image. But it's more useful to think about convolutions in this other way. I mean, this is like a sort of these are all hand-designed kernels, where they're sort of designed to perform a certain task. But a more useful way, I think, to think about kernels, at least in the context of convolutional neural networks, is that they try to identify areas of an image that are most similar to it. So for example, this is called the Sobel kernel, and the Sobel kernel has its positive values on the left side and then negative values on the right side. So before I'm going try to pause the video and think about what type of matrices when you place this kernel over would result in the highest values being outputted. The answer is similar to like how a dot product, if you know about that, to how a dot product is highest for vectors that are like similar. This is also like highest when the matrix underneath, the matrix that you're convolving with is similar. So when you do the convolution operation, this becomes highest when the image also matches the structure, where you have high pixel values on the left side and low pixel values on the right side. And what this ends up doing is if you slide this 3 by 3 filter over this image, it'll end up finding all the edges. Like it's basically a form of edge detection. Um, Now, in computer vision, in traditional computer vision techniques, there's a lot more that goes on to edge detection than just applying this filter. This is just like a very simplified view, but hopefully this gives you the intuition that kernels basically help you find areas of an image that look most like it. That's the key intuition. This is another example that also illustrates this pretty well. If you have this image here, this is our image and this is our kernel, what ends up happening is the feature map or the output that gets generated, it's highly activated for all the pixels on this sort of edge, on this diagonal, right? Like that's where it's most highly activated. And that's because those pixels match what was going on in the kernel, right? So that's where it's most similar. So that's essentially what the convolution operation is doing. Based on what the kernel is, it'll try to find areas of the image that are most similar to it. So in the context of convolutional neural networks, we don't use these sort of hand-designed kernels. Before I was talking about like the Sobel kernel, and that's like a hand-designed, like someone came up with that, right? Someone came up with that structure. It's not too hard to think of that structure yourself, but we don't want to have that sort of pre-built information being fed to our neural network. Instead, we want our neural networks to learn the values of the kernel. So the kernels are basically our weights. And the kind of beauty behind the kernels is that the same parameters get reused multiple times, right? Because you're sliding the kernel over the whole image. So when you do that, it basically you're reducing the number of parameters that you need. Don't worry too much about this line. Just talking about how to like mathematically. It's just talking about after you perform a convolution, you also apply an activation function. We'll talk more about that in the next lecture. But yeah, that's basically what we do. And something to note is that the weight values are basically trained, the kernels are trained using the same backpropagation process that we talked about in neural networks, in traditional neural networks. Now, the backpropagation process is a bit more complicated in convolutional neural network because there are some added complexities when you have this sort of structure. But yeah, it's not too different. And another interesting thing to note is that you can apply, so in like one layer, right? You can imagine that in each layer we apply a kernel or multiple kernels to an image. And let's say this is a grayscale image where each pixel value ranges from 0 to 255 and is represented by one number. Now, this is like a 2D matrix, and then let's say we want to apply multiple kernels. Each of these is going to be a 2D matrix as well. But kernels are like pretty simple in that they only detect like one type of feature, right? They like the kernel on the previous slide only detected left diagonal edge, a left downward diagonal edge, right? But what if we want to sort of like get information using multiple kernels? Well, you can do that too. What ends up happening is that you apply each kernel, right? And when you do the convolution with this image and this kernel, you'll get some feature map. And so you put that here, and then you go to the next kernel, do the same thing, and then you just stack all of the resulting outputs together. And then going into your next image, you have this sort of 3D input. going into your next layer, you have this 3D image, right? So how do you deal with 3D images? That's a good question. This is a useful question not only if our previous layers had outputted multiple dimensions, but also useful for 3D images like RGB, right? Any sort of color image has three channels: red, green, and blue. And so even then, from the get-go, we need to have a kernel that is able to deal with that. The way we do that is if our input image has multiple dimensions, like it's 3D, then how many ever channels we have here we have three channels, our kernel must also have the same number of channels, right? And when you do this, what ends up happening is, like, let's imagine you place this, let's say you place this 3 by 3 matrix here, and so it would be like this. Then all of these values in the first layer channel of the kernel would be multiplied by all the red values here. All the second ones would be multiplied by the green ones, and then all the third ones would be multiplied by the blue ones. And then you get one number here in your 1D feature map. Or sorry, this should be 2D feature map, my bad. Um, it's two-dimensional. Ignore the 1D thing. And then, this is an animation that basically shows the same process. And note that this sort of represents like one 3D kernel, but you can have multiple 3D kernels, and then you would get like another layered sort of set of feature maps, right? That's what's happening now in the animation. So now that's like one layer of a convolutional neural network, and in a full convolutional neural network you have like multiple like you have numbers of these layers where the output feature maps of one layer get fed on to the next layer and so on, and you keep performing convolutions. Now, there are some other things that we didn't talk about, like what pooling layers are and how to get to actually classify a neural network, like how to get to classification, because you know um, if you keep doing convolutions, you'll just you'll keep getting like matrices or 3D matrices. But you need to get to a point where you can say, okay, we need to classify things now. So we'll talk more about how to get to the sort of like fully connected state at the end. But in the essence, like, we've basically, the convolution operation is the at the heart of all of this. So you're set for the next lecture. All right, thank you for watching.